Hi everybody, how are you boys and girls? Okay, how are you? A warm welcome to India's most comprehensive e-learning platform, Byjus Exam Prep. So now we are in the important series called Formula 1 series, and we are discussing what network theory. Yesterday we had a wonderful session, right, on formulas, discussion of DC circuits as well as AC circuits. Yes or no, all of you? Okay. Hope you enjoyed the previous class. So please quickly respond in the comment box. Hi everybody. Hi Bhaskar Lakshmi. Good evening. Hi Reshma. How are you? Okay. Well, a warm welcome to all of you once again to this network theory. And yes, Bindu Tarangini. Hi. Hema. Hi. Lokeshwara. Hi. Okay. So yesterday I already explained about Narsimha. How are you? Good evening, Narsimha. So all of you know about my profile, but still there are certain newcomers, it looks like. Suresh is looking, new one. So let me just give my brief introduction quickly here. My name is Dr. Muninder Erukulla. I did my master's and PhD both from NIT Warangal, MTech and PhD at NIT Warangal. I have 22 years of experience. My area of interest is network theory, control systems, and power systems. I presented research articles at most prestigious IEEE and IET international conferences held at USA, Hong Kong, Malaysia, Korea, and Singapore. I visited USA, Hong Kong, Malaysia, Korea, and Singapore, presented my research articles at the international conferences. I taught more than 250 batches for GATE, ESC, and PSUs. Okay, I'm presently supervising 4 PhD scholars on the most important advanced topic called smart grid technology. Okay, using artificial intelligence techniques. I motivated more than 2 lakh students, okay, by visiting 500 plus engineering colleges and universities across the country. Okay, so you also please subscribe. Don't forget to subscribe to our YouTube channel. Okay, so that you will be getting the continuous updates. I'm going to take some important sessions in the near future. Okay, well, one more important announcement is that you have a scholarship test on 29th October at 8 p.m. Okay, if you face that exam or if you take that exam, you'll be getting up to 90% scholarship on any program that you're going to opt. Okay, so don't miss that. Okay, you just take the test. You will understand where you stand among all the competitors. Okay, well, now I saw some of the students have put some comments. Hi Rav Shankar, how are you? Okay, so some of the students put some comments that mesh analysis, node analysis, Supermesh, Supernode also they were asking. Okay, so that is why I'm starting with that particular part first, and quickly I'll finish it off, and then I'll move on to the transient analysis and two-port networks, most important topics. Okay, well, first let me go with mesh analysis. I think all of you are aware of how to apply the mesh analysis, but I'm going to explain you the inspection method, okay, by taking some different cases, how you apply. This method will help you even in the case of control systems, when any electrical system is given, when any mechanical system is given, okay, then you will be able to find the transfer function in easy manner using the inspection method. Okay, so let me give you first, I start my discussion with mesh analysis first, then I'll move on to the node analysis. I will also discuss the supermesh as well as supernode analysis. Is it okay, all of you? Fine. Now, mesh analysis, okay, first let me take the case one. First case, a simple circuit I'm taking. There are 2 loops. Generally, we select the loops, okay. How many loops are there in this? How many loops are there? Please quickly respond. Whenever I'm asking a question, please quickly respond, okay. How many loops are there? This is loop 1. This is loop 2. This is loop 3. You understand, all of you, okay? There are 3 loops. But how many fundamental loops are there? L is equal to B minus N plus 1. B stands for number of branches. N stands for number of nodes. L stands for what? Number of fundamental loops or basic loops. How many loops are there? Only 2 loops are there. Okay, this is one fundamental loop. This is another fundamental loop. Okay, Narasimha, yes, 3 loops are there. But the fundamental loops are only 2. Look at this, how many nodes are there? 1, 2, 3, 4 nodes. How many branches? 1, 2, 3, 4, 5. 5 branches, 4 nodes plus 1. How many here? 2 loops. 2 fundamental loops. Okay. But in mesh analysis, okay, you can select any 2 loops because number of loops is 2, right? The minimum number of equations required to solve the given network using the mesh analysis is also equal to the number of fundamental loops. Minimum number of equations. Minimum number of equations required in mesh analysis is equal to what, Nana? The number of fundamental loops. All of you understand this, okay? What are the minimum number of equations required to solve any given network using the mesh analysis is equal to, okay, fundamental loops, number of fundamental loops. That's it, okay? But in this, you can select, while applying mesh analysis, you can select, any loops out of these 3 loops, but you have to select only 2 loops, Nana, because fundamental loops are only 2, right? So that's why I'm selecting the first loop here. In the first case, I'm selecting loop 1 and loop 2 here. This is what the loop current, okay? But when you apply the mesh analysis, usually mesh analysis requires what, Nana? Mesh analysis, you generally apply the Kirchhoff's voltage law, but algebraic sum of the branch voltage must be 0 according to Kirchhoff's voltage law. Okay, you require branch voltages. You require branch voltages. Now these branch voltages are expressed in terms of what, Nana? Okay, branch currents. I mean, branch currents are required, right? Branch voltage, if you want, you require branch currents. Now these branch currents are expressed in terms of what? Loop currents. You understand, all of you, okay? So where is the branch current? The current flowing in R1 is, okay, I1, because this element belongs to only first loop. Look at this first loop, how it belongs, because I1 is passing through R1, R3, E1, right? Therefore, R1 belongs to only first loop. And second loop, look at this, I2 is passing through R2, E2 and R3. So R1 belongs to only first loop, therefore its branch current is same as loop current. R2 belongs to only second loop, therefore its branch current is same as its loop current. R3 belongs to both first loop and second loop, therefore its branch current is equal to, okay, the resultant of loop currents I1 and I2, I1 minus I2 in downward direction. Okay, if I take in downward direction, it is I1 minus I2. Okay, if I take in upward direction, then it is I2 minus I1. I hope you are following, okay? I hope you are following. Well, now I'm writing the equations in the loops, selected loops. What are the selected loops actually you have? These are the selected loops. Okay, these are the selected loops. Now the branch current is I1, therefore plus or minus I1 R1 is the branch voltage. Here the branch current is I2, therefore plus minus, okay, I2 R2. Therefore when I apply KVL here, I get what? Now I am taking, okay, I'm starting here and reaching the same point in the by moving in the loop, okay, in the closed loop in the clockwise direction. Then tell me here, I'm moving from plus to minus, okay, plus to minus, I'm taking fall in voltage, okay, minus to plus, I'm taking rise in voltage. According to me, fall in voltage is negative, rise in voltage is positive. That's why I'm taking minus R1 I1, minus R3 times I1 minus I2, and plus E1 is equal to 0, and take it as what? Equation 1. Similarly, loop 2 also, minus R2 I2, like this, I'm moving, right? Minus R2 I2. Again, here, when I'm taking I2 greater than I1, then the current is what? I2 minus I1. When I2 minus I1 is taken, the polarities will be plus minus. Now you are moving in this direction, you again get the fall in voltage. That is why you have negative sign. R3 times I2 minus I1, okay, plus E2. No, it's not minus E2, it is plus E2. This is actually minus E1. I'm sorry here. Yeah, this is plus E2, plus E1, and this is minus E2 because you are moving from plus to minus, that is fall in voltage, therefore minus E2. Got it, okay? Yeah. So second equation is also you got. Okay. Second equation also you got. Now I'm going to explain you the important technique called inspection method. According to inspection method, you can directly get the equations in the matrix form. You understand? Okay. You are going to get the equations in the matrix form. Got it, all of you? Okay. How do you get that equations? How do you write the equation directly? Look at this, all of you. You have two loops and two equations required. That means two variables I1 and I2. That means you get 2 by 2 matrix. Okay, this matrix is what? 2 by 2. Okay, 1 1, 1 2, 2 1, 2 2. There are 4 elements you have in the matrix. 1 1 element, 1 2 element, 2 1 element, 2 2 element. Okay, what is 1 1 element? What is 1 1 element? When you write that first term 1 1 element, what you do is, first you take negative sign. First you take negative sign. I'll tell you why you're taking negative sign. It is a predefined sign. Sir, I want to take positive sign. Yes, you can also take positive. Doesn't matter. But my practice is always negative sign. Of sum of resistances in the first loop. What are the resistances you have in the first loop? Tell me. What are the resistances you have in the first loop? Tell me. You have two resistors, 1 and 2. That is why you got sum of R1 plus R3. Okay, 2 2 element please. Again, sum of resistances in the second loop, R2 plus R3. Okay, then 1 2 element. What is 1 2 element? The common element between the first loop and second loop. What is the common element between the first and second loop? It is R3. Okay, therefore R3. But now, in the common element, how the loop currents are flowing? Look at this. The loop currents, okay, look at this. The loop currents, okay, I1 is flowing in downward direction, I2 is flowing in upward direction. Both are flowing in opposite direction to each other. That is why you maintain opposite sign to this diagonal element. That is why it is plus. Okay, similarly, this will also become plus R3 because 1 2 element is same as 2 1 element. 1 2 element is same as 2 1 element because it will satisfy off diagonal symmetry. Off diagonal symmetry means what? Now in the matrices, I think you might have already studied in your linear algebra. What is a off diagonal symmetry property? Nana says ith row jth column element is same as jth row ith column element. Yes or no? That is what I am applying here. Off diagonal symmetry is satisfied here. Okay, according to off diagonal symmetry, you will be getting plus R3 and minus plus R3 here. 1 2 element is plus R3 and 2 1 element is also plus R3. Okay, now into what do you get, Nana? I1 and I2. The variables which you have is equal to, and check in the first loop how you are touching the polarity of the voltage source. You are touching negative sign first. Therefore, you take minus E1. Okay, and how you are touching the polarity of the E2 in the second loop. You are touching positive sign first. Look at this. Therefore, you take plus E2. This is what actually you got here. Look at this, all of you. This is what the equation. Just by looking at the circuit, you can easily write for any complex network. Okay, for any complex network which doesn't contain any current sources. Okay, for mesh analysis, you can directly construct this matrix form, okay, without spending too much of time on obtaining the equations using the Kirchhoff's voltage law. I don't know anything about KCL, KVL, but I know the rules in the inspection method, diagonal elements, off diagonal elements, okay, how I am taking the voltage, everything I know very well. Understand, all of you? I can easily construct. Now, coming to the case 2, then you will understand here. Look at this. Okay, you're taking I1 here like this and I2 here like this. Okay, I1 is in clockwise direction, I2 is in anti-clockwise direction. Got it? Okay. Now, minus R1 I1 minus R3 I1 plus I2. Why? Because I1 is flowing in downward direction. I2 is also flowing in downward direction. The resulting current is what, Nana, here? I1 plus I2. Okay, when you are applying KVL in this way, the polarities will come like this. When you're applying KVL in the second loop, the polarities will come like this. Yes or no, all of you? So that is why you got this equation minus R1 I1 minus R3 times of I1 plus I2. Okay, then here negative to positive rise in voltage plus E1. Similarly, you are getting minus R2 I2 minus R3 times I1 plus I2 plus E2 is equal to 0. These are the two equations you have, okay? First equation, second equation. Shall we apply the inspection for this now? Tell me how you write the inspection, tell me. Shall we write the inspection now for this? Look at this, all of you. Look at this, all of you. Inspection. First element, I told you, negative sign. What are the elements that you have? Passive elements I'm talking about. Okay, R1 plus R3. What are the elements in the second loop? R2 plus R3. What is the common element? Common element, R3. How the loop currents are flowing in the common element? Both are flowing in downward direction, right? Yes or no? Downward direction. Both are flowing in the same direction. Therefore, whatever the sign that you have taken, predefined sign negative, the same sign should be taken for the off diagonal element. And first row, second column is same as second row, first column. That is why minus R3. And this is I1 and this is I2 is equal to, then what do you have here? You're touching negative sign first, therefore minus E1. Okay, you're touching again negative sign first, therefore minus E2. You understand, all of you? Okay, that is how you got these equations. Okay, using Kramer's rule, I1 is nothing but delta 1 by delta, I2 is nothing but delta 2 by delta, according to Kramer's rule. According to what? Kramer's rule. You understand, all of you? Okay, well. Now, case 3, Nana. Very important. This is very important. I am selecting now the another loops. Okay, two loops I am taking here. Okay, I1 and I2. The second loop I think you are understanding. Okay, I am selecting this one. This particular loop I am selecting as the second loop. Okay, well, now tell me. This element belongs to first loop or second loop? Please quickly respond. R1 belongs to only first loop or only second loop or both first and second loop? Similarly, R3 belongs to only first loop, okay, only second loop or both first and second loop? R2 belongs to only first loop, only second loop or both first and second loop? Could you please respond quickly? Any problem you have? Some buffering issue somebody saying? Ravi Shankar, are you able to follow? Okay, both. Chandu is saying both. Which one? R1, right? R1 belongs to both loops. Very good, Lakshmi. But what about R3, Lakshmi? R3 belongs to only first loop or only second loop or only, both first and second loop? Ravi Shankar, tell me. R1 both, right? Chandu, correct. But what about R3? Please respond quickly. What about R2? Please mention clearly whether R2 belongs to first and second loop, okay? Only first loop, very good. Okay, R3 belongs to only first loop. Excellent, excellent. What about R2? R2. What about R2? What about R2? Quickly, all of you. R3 only first loop, Chandu? No. R3 belongs, yeah, R3 first loop, correct. Chandu, correct, yeah. R3 belongs to only first loop, that is correct. Now, look at this. According to the loop currents representation, okay, R1 belongs to, because I1 is passing through R1, R3, E1, okay, I2 is passing through R1, R2, E2, E1, okay. So, it is very clear that R1 carries both I1 and as well as I2, and I1 is flowing in this direction, I2 is also flowing in this direction. Therefore, the branch current is I1 plus I2. Okay, but R3 belongs to only first loop, therefore it carries only I1. But R2 carries what? Only second loop. R2 belongs to only second loop, therefore its branch current is same as its loop current, that is nothing but I2. That is why the equations are very clear. I have written, I think you don't have any doubt in that, right? So, but I would like to directly give you the inspection. This is sum of the resistances in the first loop. Okay, tell me what are the elements? R1 as well as R3. Negative sign I have taken already. And what about this one, Nana? The elements belong to second loop, R1 as well as R2 according to this. Yes or no? Okay. Therefore, minus of R1 plus R2. Okay. Now, what is the common element between first and second? Obviously, what? R1. Because R1 belongs to both first loop as well as second loop. R3 belongs to only first loop according to this representation. Okay, earlier it was a common element because our loop currents were different. Yes or no? But now the loop currents are, we have taken a different way. That is why, okay, you have R1 is a common element. I am taking minus because I1 and I2 both are flowing the same direction. Okay, when both are flowing the same direction, the sign of the off diagonal element will be same as that of what? The diagonal element. So these two are the diagonal elements. Diagonal elements usually negative we are taking. That's a predefined sign I told you already. Okay. Now, coming to the first loop, how many energy sources are there in the first loop according to this now? According to this, the first loop contains only one energy source and it is touching negative sign first. That is why you're taking minus E1. Similarly, the second loop, okay, it is touching positive sign first because it is having two sources. Positive sign first it is touching and then it is touching what? Negative sign. Therefore, plus E2 and minus E1. Okay, you got these equations. So this is how the equations will come. Okay, you can easily write for any given network. You're following all of you? Okay. Very good, Chandu, Sai Verma, Bhaskar Lakshmi, very good. Yeah. Now, coming to now, case 4. Case 4, when current source is given. So far, we have not taken any current source. Suppose if any current source is given, if I select the loop currents like this, okay, if I select the loop currents like this, when I try to apply the Kirchhoff's voltage law in the first loop, I must know always the voltage across each and every element. I know what is the voltage. Because I1 is flowing I1 into R1. But this is a current source. For current source, we know the current. We do not know what is the voltage. We have to find it for an independent current source. There is no voltage availability. Yes or no, all of you? Okay. Or else, similarly here, in the second loop also, definitely you come across the current source where the voltage information is not available. Only current information is available. You understand, all of you? Okay. For that reason, we go for a different approach. First, we use the method 1, that is Supermesh analysis. According to Supermesh, the first step is, first express the loop currents in terms of the current source value. Express the loop currents in terms of the current source value. How the loop currents are flowing? I1 is flowing downward, I2 is flowing upward, current I is also flowing upward. Okay, if I take I2 greater than I1, then I2 minus I1 will be upward. I will also be upward. Therefore, I can equate them. So, I2 minus I1 is equal to I. This is the first equation. How many variables are there? 2 variables, I1 and I2. How many equations are required? 2 equations are required. So, we need to obtain one more equation. We already got one equation here. For second equation to obtain, what we do is, we suppress the independent current source. That means, we are replacing the current source by an open circuit. Its internal resistance nothing but open circuit. Tell me, what does that open circuit means? As soon as you replace it by open circuit, loop 1 and loop 2, mesh 1 and mesh 2 are getting merged. They are getting merged and forming a common mesh. That common mesh is called a supermesh. Now to get the second equation, you apply Kirchhoff's voltage law in the supermesh. by maintaining the previous branch voltages. Previous branch voltage means what? Prior to the replacement of the current source by its internal resistance, whatever the branch voltages were maintained across the resistors, you maintain the same voltages. This is what the principle of what? Superposition. Okay, sorry, supermesh analysis. Okay, what is this? Supermesh analysis. This is what the principle of what? Supermesh analysis. Now, in the supermesh analysis, if you see I1 R1, I2 R2, according to the direction of the current, the polarities are also very, very clear. Now you apply KVL by following in the clockwise direction. Minus I1 R1, minus I2 R2, minus C2 because fall in voltage, plus E1 because it's a rise in voltage. So you got second equation. Already you got first equation here. Solve these two equations, you will get the solution. This is what the standard procedure of, okay, how to apply the supermesh analysis. But I generally don't recommend this method in the competitive exam. Okay, I generally don't recommend this method. The reason is, I'm getting more number of equations here. I'm getting two equations, right? I get the advantage of the current source. The presence of the current source, I take it as an advantage and I reduce the number of equations. You see how it is going to be. Now you select the loop currents in a different manner so that the number of equations will come down. Okay, look at this all of you. Look at this all of you clearly. If you have any doubts, please put in the comment box. I'll try to clarify them, okay? Well, look at this now. The same circuit I've taken. Instead of selecting the loop currents, okay, the loop currents like this, as shown in this case 4, okay, like this. What I'm doing is, I'm selecting like this. What is the advantage I'm going to get? Look at this now. This is what I'm selecting. And I'm calling them I1 dash and I2 dash. But finally, my objective is to find I1 and I2. Don't forget that. I'll come back to that again. After finding I1 dash and I2 dash, I can also come back to what? I1 and I2. Look at this, how I'm coming. First, I'm selecting this one as what? I1 dash. This one as what? I2 dash. So it's very clear. I1 dash. This particular current source belongs to only first loop. Just now you explained that R3 belongs to only first loop in the previous example. Yes or no, all of you? Similar to that, I belongs to only first loop. That means its loop current and branch current both are same. What is the branch current? I. What is the loop current? I1 dash. Okay, but I1 dash is flowing downward direction. I is flowing upward direction. That is why I put minus sign. So I know this value. I1 dash value is known. Suppose if I is equal to 10 amperes, okay, 10 amperes given, then what is that I1 dash, Nana? 10 amperes. Without solving the loop equations, I got the answer for one of the variables. Yes or no, all of you? How many variables were there? 2. But one variable already known. Now how many variables are unknown? One more. How many equations required? One equation. You understand, all of you? If you go for supermesh analysis, 2 variables were there, 2 equations were required. But if you cleverly choose the loops, okay, if you cleverly choose the loops, then there is a possibility of reducing the number of equations. The same circuit can be solved by 2 equations. The same circuit can be solved by the 1 equation. You understand, all of you? Okay. So how do you obtain that another equation? The another equation can be obtained by selecting a loop which does not contain any current source, Nana. Okay, the loop must be selected such that the loop does not contain any current source. I hope you're all following. Okay, please respond quickly. Whether you followed it or not, please respond quickly. Now I'm selecting this particular loop which does not contain any current source. Okay, suppose if I1 is minus 10 amperes, okay, I1 dash, right? I1 dash is what? Minus 10 amperes here, right? Not 10 amperes, minus 10 amperes. Following, okay? Hema, Lakshmi, Vauma, Sai Varma, Chandu, everybody is. Repeat. Where do you got the problem? Tell me, Lakshmi. Where did you get the problem? If I is equal to 10, then I1 dash is minus 10. Correct, correct. I rectified it, okay? I rectified it, Chandu, okay? I did that mistake. It is minus 10 amperes. Correct, Chandu. Very good, Nana. Where did you get stuck? Tell me, Lakshmi. I will repeat it. Okay? Where did you get stuck? Where is the problem? Please tell me. Okay, I'll repeat it for you. Okay, look at this. When you apply the supermesh analysis, how many equations you got? 2 equations, right? But now what I'm suggesting is don't go for the supermesh analysis. Okay, temporarily you choose the loops in a different fashion such that the number of equations are reduced. Look at this. The first loop I'm selecting this one because I have a right to select any loops, right? Okay, if I select like this, suppose this is a known value. Obviously, this R1 is known, R2, E2, I, even all are known values or not? They're all known values. When they're all known values, look at this. What is the value of I1 dash? You're going to get directly I1 dash is equal to minus 10 amperes. Do you agree with this or not? Tell me first. If you agree with this, then the problem is very simple. So what I'm saying is, without solving the circuit, I come across here the value of I1 dash. I don't have to solve the equations for the sake of I1 dash. Now only I2 dash is required. Very good, Lakshmi. Okay. Now, for the sake of I2 dash, what I'm trying to tell you is, you select the loop such that that loop does not contain any current source. Got it? Okay. Look at this. That's why I'm selecting the loop like this. The loop I2 already we have, which does not contain any current source, right? Now apply the KVL here. Look at this KVL when you apply. Okay, I1 dash is a known value, but I1 dash plus I2 dash. What is the voltage across it? Minus R1 I1 dash plus I2 dash. Right? KVL when you apply, because plus minus polarities fall in voltage, I'm taking negative. Again here, plus minus polarities, the current flowing is I2 dash, therefore minus R2 times I2 dash. Here, minus E2. Here, plus E1. That's it. You got the equation. One equation is enough to solve the problem. Instead of 2 equations, you can go for 1 equation. Whereas in supermesh analysis, 2 equations are mandatory. The first equation is in terms of I1, I2. Second equation is also in terms of I1 and I2. You have to go for 2 equations. So, number of equations got reduced. Yes or no, all of you, okay? So, what are the minimum number of equations required to solve any given network using mesh analysis usually? Okay, usually it is equal to number of fundamental loops. But this condition fails when the network contains any current sources. Okay, when the network contains any current sources. The number of equations depends upon the selection of the loop currents. The selection of the loop currents. Because if you see here, if I select the loop currents, like this, okay, I got 2 equations. If I select the loop currents like this, okay, I got only 1 equation. That is what the advantage with this particular method. Select the loops in a clever manner. What is a clever manner, sir? Okay, the first loop current should pass through only current source. That value is known. The second loop current must be chosen in such a way that it does not contain any current source. So that equation is enough to solve the problem. You understand, okay? I will show you some examples, then you will understand clearly, okay? Well, now what are the minimum number of equations? I can give you a standard formula using mesh analysis. The minimum number of equations required, okay, using mesh analysis is equal to L minus, L means what? Number of fundamental loops. How many current sources are there in the earlier problem? In the previous example, 1 current source. How many loops were there? 2 fundamental loops. 2 minus 1, only 1 equation is enough to solve the network. So number of fundamental loops minus number of current sources will give you minimum number of equations required to solve the network using mesh analysis. Got it, all of you? Okay. Well, now, you got I1 dash already. Okay, that is minus 10 amperes. I2 dash if you solve the equation, then you will be definitely getting I2 dash. But I want I1 and I2. I want I1 and I2. How do I get that? I1 and I2. How do I get the I1 and I2? Because my interest is to find I1 and I2, by selecting the loop currents like this. To reduce the number of equations, I have selected like this intentionally. You understand? Okay. But I have to come back the network where the loop currents are shown I1 and I2. Okay. But whatever the loop currents you select, one principle one should not forget. One principle one should not forget that the branch currents remain same irrespective of the selection of the loop currents. You all agree with this or not? Tell me, all of you. You all agree with this or not? Tell me, all of you. Irrespective of your loop current selections, branch currents remain same or not? You all agree with this or not? Tell me, all of you. Yes. You all agree with this? Please respond quickly. Lakshmi, Saivamma, Chandu, Hema. Can you please respond quickly? Can you respond quickly? Anybody please quickly respond. The branch currents remain same. Yes, Bindu Tarangini. Very good, Nana. The branch currents remain same irrespective of the loop currents that you select. Is it okay? Very good. So what was the branch current earlier with the selection of loop currents like this? It was I1. What about this? I2. But now, with the present loop current selection, what is the branch current here? I1 dash plus I2 dash. What about here? I2 dash. So you already got I2 is equal to I2 dash. Yes or no? What about I1, Nana? I1 is nothing but I1 dash plus I2 dash. Yes or no? You take sum of these two currents, you will be getting I1. You take I2 dash, that is nothing but I2. Simply you are going to get what, Nana? I1 and I2 values after knowing the values of what I1 dash and I2 dash. If any circuit is given something like this, that I1 is equal to 10 amperes, or else, yeah, I1 is equal to 10 amperes, I2 is equal to 3 amperes. Can you tell me what are the values of I1 dash and I2 dash in this given circuit? Please respond quickly. What are the values of I1 dash and I2 dash? Given I1 is equal to 10 amperes, I2 is equal to 3 amperes, what is I1 dash and what is I2 dash? Please tell me. Quickly, all of you. Yes? Anybody quickly give the answer? Quickly give the answer. Very good. Let me check once. See, the branch current remains same, right? This is I1, but whereas this one is what? I1 dash plus I2 dash. Yes or no? So I1 dash plus I2 dash will be what? I1 is nothing but 10 amperes. What about this one here? I2 dash. This is also I2. Both are same, right? So I2 dash is equal to 3 amperes. Let me check whether it is minus 10 or minus 3. Let me check. I2 dash is 3 only, na? Why you are taking minus 3? Bindu Tarangini? From this, if you substitute here, what is I1 dash, Nana? 10 minus 3 is just 7 amperes. Yes or no? Chandu? I2 dash you got 3. Very good. But what about I1 dash? How it is 13, Nana? I1 dash plus I2 dash put together should be 10 amperes, na Chandu? Yes, Bindu Tarangini. Yes, very good. It is actually 7 amperes and 3 amperes, Nana. You understand? Okay. You understand? Very good. Okay. So let's speed up. Okay, because already we spent enough time on the mesh analysis. But these kind of problems, okay, you can expect. Giving the same network but changing the loop current selection. Okay. First circuit, the loop current values will be given, and second circuit, the loop currents values will be asked. You must be in a position to determine. Okay. Super mesh analysis I don't recommend. Select always the loop currents like this. Okay. Minimum number of equations using the mesh analysis is always what? Number of fundamental loops minus number of current sources. Simple. Well, coming to now node analysis quickly. Okay. Node analysis quickly. Node analysis quickly here. Okay. This is what the circuit given. The number of nodes always you try to minimize the number of node selection here. You don't take the node here because these two elements are connected in series. The degree of node is 2. Okay. Whenever you want to take a variable at a particular node, you make sure that the degree of that particular node is minimum 3. Minimum 3. You understand all of you? Okay. The degree means what? Number of elements connected at that particular node. Degree is nothing but number of elements connected at that particular node. The degree is 2, therefore I don't take this variable because the elements are connected in series. The degree is 2 here, I don't take a variable. The degree is 2 here, I don't take a variable. But I take the variable here because the degree is 1, 2, 3, 4, therefore I take a variable here. So first node, okay, that is called the principal node. This is also second node because the degree is 3. The degree is 2, therefore I don't take a variable here. The degree is 2, I don't take a variable here because the elements are connected in series. The degree is 1, 2, 3, 4, 5, therefore I take a variable here. You understand all of you? Okay, 3 nodes are there. Minimum number of nodes to solve this network required is 3, but out of which 1 node is selected as a reference node. Generally the bottom node is selected, but it is not compulsory. Okay, but usually bottom node is selected. It is a common practice. Therefore, these two are called principal nodes. Therefore, this is V1, this is V2. 2 variables are required. 3 nodes, 1 node is gone for the reference node. 2 principal nodes, 2 variables are required. 2 equations are enough. Minimum number of equations required to solve the given network using the node analysis is n minus 1, where n is the minimum number of nodes required. Okay. Well, so V1 and V2, right? So this is what the circuit you have. This is V1, this is V2. Okay, I can write the equation here directly. Using inspection also I'll tell you, that is very important. That will be helpful in the control systems topic also while finding the transfer function for any given circuit. Okay. Yes, Saivamma, you got 7, huh? Okay, fine, no problem. 7 amperes and 3 amperes. I hope you got that. Well, now look at this. While applying KCL at node 1, you select V1 is greater than V2. V1 is greater than V2. Now look at this. Whenever you apply Kirchhoff's current law at node 1, KCL must be applied, right? KCL at node 1, you make sure that current through each and every branch is available, right? So you need to find the current here, you need to find the current here, but it's already available. You need to find the current here, you need to find the current here. Assume that all the currents are leaving away from the node, okay, except the current sources which are provided already, okay, because already that current is injected by the current source. Now, assume that this voltage V1 is higher than any other node voltage, so that every branch current will be leaving from that particular node. Now here is what a resistive element. You need to find the current through that element, right? So this is V1 with respect to this reference node. Now when you take this is 0, obviously this is going to be E1. You all agree? This is E1. Then what is the potential difference between these two? V1 minus E1. If I take V1 greater than E1, V1 minus E1. So what is the current then? The current is V1 minus E1 by, according to Ohm's law, this is by R1. So this is how you got this current flowing through that branch, and that current is leaving from the node. I am taking it positive. Entering current negative, leaving current positive. I4 is entering, that is by minus I4. Similarly here, when this is 0, the voltage at this point is E4. The potential difference across R4 is plus minus V1 minus E4, and the current is going to become what, Nana? V1 minus E4 by R4. That is how you got this current. That is how you got this current. V1 minus E4 is a potential difference across R4. V1 minus E4 by R4 is the current flowing through the R4. Right? Now, next, here. Now coming to here, I'm just removing all this again. Yeah. Yes, this is 0 and this is V1. I want to find the current in this particular element. There is a resistive element. Always find a resistive element in the path where you are trying to find the current. That will be easy way of analyzing the given network. So I'm interested to find the current in this particular element or in this particular branch. So first let me search whether this branch containing any resistive element or not. Yes, it is having. So find the potential difference across it. Then apply the Ohm's law. That's how you get the current easily. Okay? Well, tell me now here, what is the voltage at this point? V1. Yes or no? What is the voltage at this point? You tell me. It is already V2. You jump from this point to this point. You're jumping from lower potential to higher potential. When you jump from lower to higher, there is an increase in voltage. You take the voltage. That means E3 must be taken. Okay, this value is V2 plus E3. The voltage at this point is what? V2 plus E3. The voltage at this point is what? V1. What is the net potential difference? V1 minus V2 plus E3. That is why you got V1 minus V2 minus E3. That is what the potential difference across R3 divided by R3 will give you the current flowing through that particular path. How you remember, that is of your problem, but this is how you get V1 minus V2 minus E3 by R3 is the current flowing in that particular path. Okay, the current flowing here is R5 is there. Don't put V2 by R5 because current source is connected in series here. Irrespective of the resistance value, the current all the time flowing in this particular branch is I5 all the time. All the time. You understand, all of you? Okay. Therefore, don't find again the current by using V2 by R5. In fact, V2 is not the voltage across R5. V2 is the voltage across the series combination of V2 is the voltage across series combination of R5 and I5. Nana. You understood, all of you? Okay. Well, so this is how you are going to find. So the current here is I5 and the current flowing here, this is 0. Since the polarities are minus plus, the voltage at this point is minus E2. The potential difference is what? Plus minus V2 minus of minus E2 plus E2. Okay, this is nothing but the potential difference across R2, and the current flowing through that one is V2 plus E2 by R2. So now I am getting that equation plus I5 because the current is leaving. Okay, plus V2 plus E2 by R2, the current is leaving. Okay, V2 minus V1 plus E3 by R3 by taking V2 greater than V1. That's why you got this particular term in the equation. This is equation 2. This is equation 1. You understand, all of you? Okay. Well, now I'm using the inspection. Now I'm using the inspection. You understand, all of you? Okay. Inspection. How do you use it? Again 2 by 2 matrix because there are 2 variables. Yes or no, all of you? There are 2 variables. I'm getting what? 2 by 2 matrix. The first one element is, okay, I'm taking positive sign as a predefined sign in the node analysis. According to my convenience, I'm selecting that. You can take negative also. Then the convention will become completely reverse, okay? But I'm following the positive terminal I'm taking. I mean positive sign I'm taking for all diagonal elements. Whereas in mesh analysis, I'm taking negative sign for the diagonal elements. But here in the mesh analysis, I'm selecting what? Positive sign for the diagonal elements. That is a predefined sign. Predefined sign can be anything actually, but I'm taking positive for my convenience. Now tell me here. Sum of conductances at node 1. How many conductances are there? According to inspection method, sum of conductances. Sum of conductances. Look at this. At node 1, 1 by R1 is a conductance, 1 by R3 is a conductance, 1 by R4 is a conductance. At node 2, 1 by R2 is the conductance, 1 by R3 is the conductance, but I do not consider this because it is in series with the current source. Any element in series with an ideal current source can be neglected, Nana. Any element in series with an ideal current source can be neglected because, okay, because irrespective of the value of that particular element, it will always carry the current source value only. That is why we can neglect it. Okay, so that is why you see 1 by R2 plus 1 by R3, here 1 by R1 plus 1 by R3 plus 1 by R4, because I am dealing with conductances. Conductance is nothing but reciprocal of resistance. You're all following? Please respond quickly in the comment box. If you have any doubts, I'll repeat again. Please respond quickly. Okay, following right? Following right? Very good. Very good, very good. Right. Now, what is the common element between the first and second node? First and second node, what is the common element? I'm talking about passive element. R3 only. Take the reciprocal because the conductance. That is why you got 1 by R3. But take opposite sign to the predefined sign. If you take plus here, you take minus here. If you take minus here, you take plus here. But I generally take, it's my common practice, it is a positive sign, it is a negative sign. Okay, very good Chandu, very good Bintarangni, very good. Okay, very good. So this is what off diagonal element and first row, second column is same as what second row, first column. That is why according to off diagonal symmetry, the 2-1 element will also be same as what? Okay, 1-2 element. That's it. So V1, V2 is equal to, now this is very interesting, look at this all of you. At node 1, you see there are 4 branches connected. 1, 2, 3, 4. 4 branches connected. I start with the first branch. Okay, at node 1. Okay, if I assume that V1 is greater, then the current leaves and touches positive sign first. Therefore, plus E1 by its internal resistance must be taken plus E1 by R1. Next, I4 is entering current. Usually entering current is negative, but outside we are writing, therefore I take plus I4. I have to remember it. Inspection method means what? There are certain rules we have to remember. There are certain rules we have to remember. Okay? I have to remember this. Got it? Okay. Next. This branch, V1 is greater, I am assuming, then current leaves. When higher, current always flows from higher potential to lower potential. Current leaves and touching positive sign first. Therefore, plus E4 by its internal resistance. Any resistive element which is in series with an ideal ideal voltage source can be considered to be an internal resistance. There is nothing wrong in that. So E4 by R4. E4 by R4. Got it? Okay. Next. Current is leaving and touching positive sign first. Plus E3 by R3. Okay. Plus E3 by R3. That's it. 4 terms you are getting on the right side. At second node, let us investigate now. At second node, let us investigate now. Okay. Current V2, from V2 higher potential to lower potential, I am assuming that V2 is higher. Okay, that's an assumption. V2 from current flows from higher potential to lower potential. It is going and touching negative sign first. Minus E2 by R2. Minus E2 by R2. Minus E2 by R2. Okay. Again, if I assume that V2 is higher, then current flows from V2 to V1, then touching negative sign first. Minus E3 by R3. Minus E3 by R3. Okay. Then current I5 is leaving. Usually I5 leaving means positive on the left side, but I am moving it to the right side. Minus I5. I have to remember it. I have to remember it. This is called inspection method. Once you have this matrix form, you give me any complex network, any large scale network, whether it is AC network or DC network, it doesn't matter. You give me any mechanical system or electrical system, doesn't matter. I can construct directly this matrix form just by looking at the network, remembering all the simple rules in the inspection method. I can directly construct the matrix form. This method is called inspection method. Okay, it can save a lot of time, I'm telling you, if you can practice. While explaining, it looks like, lengthy, bigger, but it is a very simple technique and easy to remember. Okay, in no time you can obtain the matrix form. Got it, all of you? Okay, well, very good. Okay, so then using Cramer's rule, you all remember, I think, Cramer's rule, V1 is equal to delta 1 by delta, V2 is equal to delta 2 by delta. That's it, right? Very good. Now suppose if I change the reference node position, I am selecting this particular node as a reference node. There is nothing wrong now. Any node can be selected as a reference node. Any node can be selected as a reference node. If I select this one as a reference node, this is V1, this is V2. I'm directly constructing the matrix form inspection method using. Now first element, one element will be having what? 1 by R1, 1 by R4, 1 by R3, right? That is what you have. Second node, this is what the second node now, V2. It is having now 1 by R1, 1 by R4. I should not take this because it is in series with the current source, and 1 by R2. Look at this. 1 by R1, 1 by R2, 1 by R4. What is the common element, or what are the common elements between first and second? Look at this. Between V1 and V2, there are two passive elements, R4 as well as R1. That is why I am selecting here 1 by R1 plus 1 by R4. Predefined sign is plus here. Yes or no? Predefined sign is what? Here plus for diagonal elements. For off diagonal elements is negative, right? Okay, first row, second column is same as second row, first column. Because of off diagonal symmetry, mesh analysis, node analysis, when you obtain the equations, obviously those equations will satisfy off diagonal symmetry. Nothing but ith row, jth column element is same as jth row, ith column element. Chandu is asking one doubt, sir, if between V1, V2, E3 is not available, then what should we do? No problem. E3 is not there, then what will happen? This right side quantity won't appear. This right side quantity won't appear. The E3 is 0. Okay? No worry about that. Right? Okay. Now, at first node, how many branches are there? Tell me here. At first node, how many branches? 1, 2, 3, 4. You got it, Chandu? Okay. So, again, touching positive sign first plus E1 by R1. Touching positive sign first plus E4 by R4. Touching positive sign first plus E3 by R3. And I4 generally entering current negative this side, but I am setting that side. It is actually becoming what positive. Therefore, you got here, look at this, E3 by R3, I4, E1 by R4, E4 by R4. This is a printing mistake. E4 by R4 will also come into picture. You understand? Okay. Got it? Very good. Now, second node again. Second node, what are connected here? 1, 2, 3, 4, 5. 5 terms should come in that particular right side component. Okay. In the matrix, that is 2 by 1 matrix. Okay. You need to get the second element, right? Look at this now. Right. Minus E1 by R1. Minus I4 because it is leaving now. Leaving current is positive on the left side, but right side is negative. Minus E4 by R4. It is now entering as far as this V2 is concerned. Negative on the left side, but positive on the right side. Plus I5. Touching again here, positive sign, therefore plus E2 by R2. Look at this now. Minus E1 by R1, minus I4, minus E4 by R4, plus I5, plus E2 by R2. Simply just, I construct this entire matrix form easily by just using the inspection method, by remembering the rules. Okay, you practice more, you definitely fix that particular method in your mind. You can easily solve, you can play with the networks, I'm telling you. You can play with the networks. Got it, all of you, okay? I think all of you understood this. Please respond quickly in the comment box, okay? Right. So you have a doubt when we compare these two circuits. For example, I take this node as, because there are 3 nodes, right? There are 3 nodes, right? There are 3 nodes. There are 3 nodes. I'm selecting this node as a reference node. In this example, you see, this node as a reference node. There are 3 nodes. This node is selected as a reference node. Yes or no? Assume that you solve the problem and you got finally this V1 is equal to 10 volt, V2 is equal to 7 volts. But now I am interested to find the voltages at these 2 nodes by taking this bottom node as a reference node. Is it really possible or not? Is it really possible or not? Okay. Chandu, can you tell me, is it possible to find the other 2 node voltages by taking this bottom node as a reference node? Yes or no? Hema, please tell me. Chandu, Sai Verma, Bidutarangni, Bhaskar Lakshmi, Reshma, can you respond, Anna? Can you respond? You can find or not? Yes, possible. Very good, very good, very good. Yes, possible. Look at this, what are those values? The difference between these 2 cases is what? Just only selection of the reference node, right? Only selection of the reference node. Okay, now, if I want to get this particular case, I have to convert this particular node into reference node. That means what? I have to make it 0. If you want to make it 0, this particular node voltage must be reduced by what? 7. Because 7 minus 7 will become 0. So this node voltage must be reduced by 7. If one node voltage is reduced by 7, if one node voltage is reduced by 7 volts, then all remaining node voltage will also be reduced by the same voltage or not. That's what I'm applying here. Already it was 10 volts. Because it is converted to reference node, 10 minus 7, it will become 3 volt. It was already 0 earlier. It becomes 0 minus 7, it becomes minus 7 volts. Now I got V1 dash is 3 volts, V2 dash is minus 7 volt. Finally, look at the potential difference between these 2. 10 minus 7 is what? 3 volts. Look at this, 3 minus 0, it is 3 volts. Yes or no? Okay. The potential difference between these 2, if I take 0 is higher, 0 minus 7, minus 7 volts. Minus 7 minus 0, minus 7 minus 0, minus 7 volts. The potential difference between these 2 nodes, 10 minus 0 plus minus 10 volts. Here also 3 minus of minus 7 plus minus 3 minus of minus plus minus 10 volts. That's what you are getting. That means any node can be selected as a reference node. There is no restriction. Understand all of you, okay? And the node voltage might be anything. It need not be 0. It may be any other value. Understand all of you? But for convenience, we are selecting it as 0. You understand all of you? Suppose if you select this one is 0, then you got this is 10 volts and 2 volts. Suppose if you increase this particular voltage by 3 volts, okay, then what will happen here? It becomes 13 volts. It becomes what? 5 volts. Every node voltage will be, if you are taken 0, then you got 10 and 2, 10 and 2 volts here, right? 10 and 2 volts. But if you had selected the reference node voltage as 3 volts, what would have been the other node voltage, Nana? 10 plus 3 and 2 plus 3. That's it. Simple. 5 volts and 10 volts. That's it. Got it, all of you, okay? Now, another important case, last case in the node analysis. With this, I can wind up the node and mesh analysis and move on to what? The transient analysis by taking some examples, okay? This is what the problem. Another simple case. Very important case. Yesterday someone asked in the comment box. By looking at that, I'm actually trying to discuss, okay? Yeah. Tell me now. Okay? First method, look at this. If you can observe the network, one difference you must find here. Okay? This is a 1 voltage source which has a series resistor. This is a 1 voltage source which has a series resistor. But this voltage source doesn't have any series resistor. This is a special case. Whenever the network contains an ideal voltage source which doesn't have any series resistor and you are trying to apply node analysis, it is a special case. These kind of special cases can be handled in 2 different ways. The first method is supernode analysis. First method is what? Supernode analysis. Look at this here. According to supernode analysis, I am selecting again, this is V1, this is V2, and this is the bottom node as a reference node. Okay. The current flowing through this particular path is not available because there is no resistive element. Directly, you do not know what is the current flowing through this. You know the current flowing through this, right? Because it is V1 minus E1 by R1. You know current flowing through this. It is V2 minus E2 by V2 minus E2 by R2. Do you know what is the current flowing through this? V1 minus V2 minus E3 by, you don't know what is the resistive element. The resistive element is not there. And you can't say the resistive value is 0, therefore infinite current is flowing. Infinite current never flows. Infinite current flows only in one particular aspect. That is when KVL violation takes place. That means it is an invalid circuit. Infinite current, infinite voltage never appear in the given circuit, Nana. That is wrong. So, there is some current flowing, actually the finite current, but we do not know how to find it. That is the biggest problem you are having. Okay, for that reason you are applying the supernode analysis here. According to supernode analysis, first step is that you express the node voltage in terms of the voltage source value. This value is known value, right? Some 10 volts, let us say. V1 minus V2 will give you the polarities plus minus because V1 is higher. And E3 is also having the same polarities. Therefore, V1 minus V2 is equal to what? Plus 10 volts. So you got that V1 is minus V2 is equal to E3. You call it equation 1. You call it equation 1. Then what you do is, just like in the supermesh analysis, how you suppress the current source. Now here you suppress the voltage source. That means replace the voltage source by its internal resistance. The internal resistance of an ideal voltage source is 0. 0 volts refers to short circuit. This is what the short circuit you have. As soon as you replace it by the short circuit, that E3 is replaced by the short circuit, then node 1 and node 2 are combined. Both are looking like operating at same potentials. Both nodes are merged. So this particular node is forming a common node. The common node is nothing but the supernode. Now, you require another equation because there are two variables V1, V2. Already you got one equation. To get another equation, you apply Kirchhoff's current law at supernode. You apply KCL at what? Supernode. So I'm applying KCL at supernode. But when you apply KCL at supernode, maintain the previous branch currents. What was the branch current flowing here? V1 minus E1 by R1. What was the branch current here? V1 by R4. What was the branch current here? V2 by R5. What was the branch current here? V2 minus E2 by R2. The same branch currents you are maintaining. For supernode, there are 1, 2, 3, 4 branches connected. You got that equation consisting of 4 terms. V1 minus E1 by R1, V1 by R4, V2 by R5, V2 minus E2 by R2 is equal to 0. 2 equations, 2 unknowns. You can solve them. You get the values of V1 and V2. Is it clear, all of you? This is what the supernode analysis. But I don't recommend the supernode analysis. Supernode must be applied only under unavoidable condition. That condition also I will tell you. Instead of supernode, you apply the reference node shifting method. This method is not mentioned in any textbook, Nana. Okay, out of my experience, after solving several problems, okay, I'm suggesting and recommending this particular method. Okay, I actually, with lot of practice, I'm able to explain you this particular method. Understand, all of you? Okay, this method I have literally invented to make the problem simple and solve the given networks, because our ultimate objective is to save the time in the competitive exams, right? That is why I just found this particular method, okay, to reduce the number of equations. The number of equations decreases, then the computation time will also decrease. So please focus on this, how we solve, okay, with less number of equations as compared to the supernode analysis. Look at this, all of you. So far it is very clear the concept, right? All of you please respond quickly. So far the concepts are very clear, right? Please respond quickly. Chandu, clear. Lakshmi, clear, okay. Reshma, very good. Okay, now let's see Nana. I'm actually shifting the reference node. I already explained you that any node can be selected as a reference node, right? Out of these three nodes, I'm selecting this particular node as a reference node now. Look at this particular node is selected as a reference node. When you select this one as a reference node, because this is a known value, say this is 10 volts, negative side you are taking a reference node, then obviously positive side this voltage becomes what, Nana? 10 volts. You agree with this, all of you? First you tell me. You understood that step? Please respond quickly. Is there problem related Supermesh in GATE exam, sir? No. See, nobody will ask you to apply Supermesh or Supernode, Nana, Bhaskar Lakshmi. Try to understand. When problem is given, okay, some people choose Supermesh because they know Supermesh to solve the network. There they will do a mistake, I'm telling you. So nobody will ask you in the GATE that you apply this method, that method. After explanation of all these methods, you must understand that which method is the best for a given problem. Then based on that you have to solve the network. You understand, Lakshmi? Okay. Well. Right. Clear? Very good. Look at this now. When you select this one as 0, this value is known. Out of 3 nodes, one node I have selected reference. As soon as I select it as a reference node, the second node value is also known value now. Out of 3 nodes, now only one particular node voltage is not known. So how many equations are required to solve this network? Actually, you have minimum number of nodes required 3. If one is gone for the reference, usually 2 equations are required. This is what generally when the problem is given, minimum number of equations required using node analysis means generally the answer is 2. But look at this. 3 nodes are there, but 1 equation is enough because this is reference, this is a known value. This is only unknown value. 1 equation is enough to solve the problem. I am applying now KCL at this node, Nana. Look at this. Okay, V minus E3 plus E1 by R1 is the current flowing through this. This is what the term. V minus 10 volts plus E1 by R1. Okay, E3 means known value. Next, here, V minus E3 by R4. This is another term. V by R5, V minus 0 by R5. This is another term. V plus E2 minus 0 by R2. V plus E2 by R2. You are following, all of you, this particular equation? Only one equation, you solve the problem. That's it. Got it? Okay. You understand, all of you? Please respond quickly. Hope you followed this, right? Okay. Hope you followed this, all of you. Please respond quickly. Okay. Now look at this. I told you already that by taking this one as 0, you got this one is 2 volts. Okay. And this one is, let us say, 10 volts. Assumption, okay. After solution, you got 10 volts. But I want the solution by taking this one as 0. Then obviously what happens, you are converting this particular node into reference node. That means this node voltage is reduced by 10 volts. Then every node voltage is reduced by the 10 volts. Already it was 2, therefore 2 minus 10, this is minus 8. It was 0, 0 minus 10, nothing but minus 10 volts. That's it. Simple. Instead of taking 2 equations, I shifted the reference node. After that, finally, my answer is supposed to be what? By taking this bottom node as a reference node, I am supposed to answer the voltage at the other 2 nodes, Nana. But I got this one by reference node shifting method. I can convert easily. The conversion is quite possible. Just now we have discussed in the previous example. This is how supernode analysis can be applied, eliminated. Eliminate always supernode analysis. Many people go for the supernode analysis. Whenever there is a voltage source that they come across here, simply they go for the supernode analysis. I don't recommend that method. Supermesh analysis also, I don't recommend that method. Okay. Usually, most of the problems, 99% of the problems can be solved with the node analysis. And out of that, Most of the problems can be eliminated supernode analysis. Very few where you cannot avoid or escape from the supernode. I'll tell you that. That is why I explained the supernode analysis also. Okay? Yes. Examples let us see now. Then you will understand. Examples let us see now. Then you will understand. Then you will understand. What are the minimum number of equations required to solve this network using mesh analysis? Simple mesh analysis means how many loops are there? 1, 2, 3. How many current sources are there? 2. So 3 minus 2, one equation is enough to solve this network. How many minimum number of equations required using node analysis? 1, 2, 3. One bottom node can be taken as 0. Okay, whenever you decide this, first you check whether there are any ideal voltage sources without any series resistor. At that point only, n number of nodes, n minus 1 equations will violate. Okay, this is a voltage source but has a resistor. This is a voltage source but has a resistor. So no worry. 3 nodes are there. 3 nodes means, okay, 2 equations. 3 minus 1, 2 equations. So who is giving the minimum number of equations for this particular problem? Mesh analysis. Who is the best method? Mesh analysis for this particular problem. You understand, all of you? According to me, the best method means a method which gives less number of equations is called the best method. Okay? So mesh and minimum number of equations required to solve this network means minimum of mesh analysis comma node analysis. That is nothing but what, Nana? 1 only. That you can achieve through mesh analysis. I hope you understand the point. Okay? So mesh analysis will give you 1 equation, node analysis will give you 2 equations. The minimum number of equations to solve this network, okay, is just 1. That you can achieve through mesh analysis. That is how you need to answer. Now coming to this particular problem. Minimum number of equations required to solve this network. First, let's proceed with mesh analysis. 1, 2, 3 loops. 3 current sources, 3 minus 3, 0 equations required to solve this network. The time is not there, otherwise I would have shown you by taking some numericals also. Without solving even a single equation, I can solve this problem using mesh analysis. You understand, all of you, okay? The time is not there, but if you, I will definitely clarify in case if you have any numericals by taking some random numericals and solve it. And you have any doubt, my Telegram group channel is there already, right? Professor Muninder Gate. Okay, I give you that once again. This is what my Telegram channel group, okay? Telegram channel group. You can join and you can post by taking the same circuit, by taking some numerical values, okay? You solve it. Then let me know if you have any problem. I will clarify your doubt. Got it, okay? Very good. Very good, very good. Heina Suma. Very good, okay. So, minimum number of equations using mesh analysis is 0 now. What about node analysis, Nana? Can you please tell me? Node analysis. 1, 2, 3. This is 0. So, V1, then V2. Then 3 minus 1, 2 equations. Mesh analysis will give you 0, node analysis will give you 2. Minimum number of equations required to solve the network is what? 0. If somebody asks the questions, what are the minimum number of equations required to solve the network using mesh analysis? 0. Using node analysis, 2. Simply without mentioning any analysis, any method, what are the minimum number of equations required to solve this network means minimum of mesh analysis and node analysis, nothing but what? 0 only. Minimum of. Hope you understand the point. Coming to this now. 1, 2, 3. Mesh analysis will give you 3 loops but 1 current source, 3 minus 1, 2 equations. Node analysis 1, okay, 2, 3, 3 minus 1, node analysis, 3 minus 1, 2 equations. Mesh and node both will give you equal number of equations. Therefore, minimum number of equations required to solve this particular network is what? 2. Now coming to this now. Another interesting question. 1, 2, 3, mesh analysis will give you 3 minus 1 because there is one current source, 2 equations required. Node analysis, look at this 1, 2, 3. Node analysis, don't say 3 minus 1 because there is a current source which doesn't have any series resistor. Current source which doesn't have any series resistor. Don't go for supernode analysis. Supernode will give you definitely 2 equations, but I am giving what reference node shifting method. If I take this one as 0, if this is 10 volts, this will become 10 volts. This value is known, this value is known, only this value is not known. Therefore, one equation is enough to solve this network. Literally, there was one question in the gate, okay? There was one question in the gate. I can give you the gate question also. I can give you the gate question also. What are the minimum number of equations required to analyze this particular network? Okay, this is what the problem given. You tell me now here, if you go for mesh analysis 1, 2, 3, 4, right? 1, 2, 3, 4. 4 equations required using mesh analysis. But node analysis you see, okay, 1, 2, 3, yes or no all of you? But this is the voltage source which doesn't have any series resistor. If I take this one as 0, this value is known or not? This is a known value. If it is 10 volts, it is also 10 volts nana. Yes or no? Then if this is 0, this is 10 volts, only this particular value is not known. Therefore, only one equation is enough to solve using node analysis. I hope you understand the point. Literally this question, this kind of question was asked in the GATE examination. You understand all of you? Okay. So that is why I'm telling you, I'm teaching all these things for a reason that there were some previous years questions that you can observe in the GATE based on this concept. Okay. Only one question was asked so far, but doesn't mean that you can neglect it. We don't know which question comes from which direction. That is a GATE examination. Don't forget that. Okay. Well. So now I think you understand clear, right? Minimum number of equations required to solve this network is what? 1. The earlier example I told you that in the GATE, 4 equations required for mesh analysis and 1 equation is required for node analysis. Yes or no? Then minimum number of equations required to solve the given network means minimum of this number of equations of mesh analysis and node analysis, that is nothing but 1. That was literally the answer. Understand all of you? Okay. Well, now coming to this now. This is another beautiful example. How many equations are required to solve the network? Mesh analysis 1, 2, 3 loops. There are no current sources. Then obviously 3 equations are required. Node analysis, but there are 2 voltage sources. One is 10 volts, the other is 5 volts, let us say, okay, which do not have any series resistors. It's a golden opportunity for you. Try to escape from the supernode to the possible extent. Suppose if I take this one as 0, there are 4 nodes, right? Totally 4 nodes. If I take this one as 0, this is 10 volts. I don't need to solve for this node, but there are 2 more nodes left over. This is V1 and V2. This is a super node. 2 equations required. Okay, 2 equations required. That is a super node. In order to escape from the super node, what I can do is I select now this node as a reference node. Obviously this will become 5 volts, but here these 2 are now the principal nodes. This is forming the super node. You understand all of you? This is forming the super node. Then what is happening here? Sometimes you cannot escape from the super node even if you shift the reference node from the bottom node to any other desired location. Still you will be facing the supernode. That is why I told you that supernode analysis is also very important. But to the possible extent, you try to avoid it. There are most of the cases you can avoid it, except this kind of cases. Understand all of you, okay? If you take this one as 0, this is forming supernode. If you take this one as 0, this is forming a supernode. So you have to go for supernode, that's it. Now this particular example also you can see, 0, 2 nodes, okay. Mesh analysis 1, 2, 3, 4. Mesh analysis will give you what? 4 equations. Okay, node analysis will give you 3 nodes. Don't come to any conclusion 3 minus 1, 2 equations. This is actually 10 volts, let us say. If you take this one 0, it doesn't have any series resistor, it becomes 10 volts. Only one equation is enough now by using reference node shifting method. Only one equation is enough to solve this network. Is it clear now, all of you? Okay, minimum number of equations required to solve the network is what? Just one. Using that you can achieve through node analysis. Please put, your doubts in the comment box. I hope if it is very clear, please respond in the comment box if it is clear. Let's move on to another important topic. Transient analysis, important formulas. In node analysis, mesh analysis, there is nothing like formulas actually. It is complete analysis. I have to discuss analysis only. No formulas at all in node analysis, mesh analysis. Because someone actually mentioned in the comment box, I gone through, okay? And I try to explain, I try to spend much amount of time on the mesh and node analysis. But transient analysis, the formulas point of view, very simple. Analysis point of view is a bigger one. I already gave some lectures in the transient analysis in a detailed manner. I will share once again in my Telegram group those 5 lectures or 6 lectures that I have taken once again. Understand all of you? If you find in the group, you can please go through that. Okay, the newcomers who joined recently, probably you may face the problem in accessing those videos, but I will share once again. The transient analysis in detailed manner, I have taken YouTube sessions. Okay, very, very detailed manner I have covered. You understand all of you, okay? But node mesh analysis I have not taken so far. That's why I spent some time here. But of course, I'm going to solve several problems in the near future on node and mesh analysis using some, the simple techniques which we have explained. We are going to apply on the given problems by taking some previous year's questions also, okay? Well, so in the transient analysis, first I would like to start with inductors and capacitors, Nana. First, I would like to start with what? Inductors and capacitors. Because inductors and capacitors characteristics, if you do not know, there is no point in understanding in the transient analysis. You understand all of you? Okay, well. Now, coming to this here. First, capacitors I start with. Q is equal to CV, you know very well. Where C is equal to alpha epsilon naught by D. Alpha is the cross-sectional area. Epsilon naught is what? Permittivity. Okay. I of t is equal to C dV of t by dt. And I told you even in yesterday's class also this formula, I don't want to explain again. This is the slope, this is the area. V of t is equal to V of t naught plus 1 by C integral t naught to t I of t dt. Power can be calculated. Voltage and current product. Voltage is V of t, current is C dV of t by dt. And once you know power, you can find the energy by using this simple formula. Okay, you will be getting W of t naught is nothing but initial energy. 1 by 2 C into V of t square minus V of t naught square. Where t naught is what? Initial voltage. V of t naught is nothing but what? Initial voltage. V of t is what? Final voltage. So what is the energy stored in the capacitor, okay, between the intervals t naught to t is W of t naught, nothing but initial energy, plus half of C into V of t whole square minus V of t naught whole square. Suppose if initial voltage is 0, simply you can express half CV square. That's why most of the times we remember the formula half CV square by neglecting the initial energy W of t naught, by also neglecting that V of t naught. Okay, that is why you got this formula half CV square, simply half CV square, right? Okay. Now, the important property is that a capacitor is open circuit to DC. When DC is given, capacitor is acting like open circuit. A capacitor blocks low frequency signal because open circuit, right? Open circuit means blocking. DC is a low frequency signal. Capacitor blocks low frequency signal and passes the high frequency signals. That is why we use this capacitor in the filters. Voltage across the capacitor may not change instantaneously. Very important, Nana. Voltage across the capacitor may not change instantaneously, abruptly, suddenly. Current through the capacitor may change instantaneously. Current through the capacitor may change instantaneously. Since the voltage across the capacitor may not change instantaneously, the discontinuous voltage may not be accepted by the capacitor. The discontinuous voltage may not be accepted by the capacitor. What do you mean by discontinuous voltage? For example, if I give you this voltage, is it really acceptable by the capacitor, Nana? All of you please quickly respond. Vc of t if I take, will it accept suddenly? Will it accept this particular voltage? Is it a continuous voltage or discontinuous voltage? Please quickly respond, all of you, in the comment box. Is it a discontinuous voltage or continuous voltage? Please quickly respond, all of you. All of you please respond quickly. Lakshmi, Hena Suma, and Sai Verma, Chandu, Hema. All of you please quickly respond. Continuous or discontinuous? Please quickly respond, all of you. Enesuma, okay, do not accept this that voltage, okay, I agree, but tell me whether it is discontinuous or continuous. All of you please respond. This particular voltage is a discontinuous voltage or continuous voltage? What about this particular one? Second one, continuous voltage or discontinuous voltage? First one is a discontinuous voltage. Look at this, suddenly changing from this value to this value. In zero time it is changing. Very good, Chandu, discontinuous. But this is continuous. There is no sudden change. Gradual change is there. Very good, Lakshmi, you understand now. You mentioned initially it is a continuous. Okay, it is a discontinuous. The voltage is changing from one value to other value suddenly in zero time. The voltage, suppose you apply across the capacitor, the voltage across the capacitor may not change instantaneously. Therefore, the capacitor does not accept the sudden change in its voltage. Okay, so therefore, voltage across the capacitor may not change instantaneously means a discontinuous voltage may not be accepted by the capacitor. But a continuous voltage may be accepted by the capacitor. A continuous voltage may be accepted by the capacitor. You understand, all of you? Okay, a continuous voltage may be accepted by the capacitor. Discontinuous current may be accepted by the capacitor. There is no problem for the current actually. The problem is with only voltage. Discontinuous voltage may not be accepted by the capacitor. That means voltage across the capacitor may not change instantaneously. But current through the capacitor may change instantaneously. That means discontinuous current may be accepted by the capacitor. That's it. It's very clear, okay? 1 mark questions. Which of the following statements are true or not true or is true, is not true? You understand? Be clear. Formula is not just only formulas. The conceptual questions come under the formulas also, right? Okay? You must remember this. An ideal capacitor does not dissipate the energy. An ideal capacitor does not dissipate energy because there is no resistor. A real and practical capacitor will definitely have a resistive element. Generally, the practical capacitor is modeled as with a parallel resistor model. So definitely where there is a resistor, there is a dissipation. It will dissipate the energy. Now, series combination of the capacitors. I told you yesterday, the conductance formulas and capacitor formulas are same. Inductance formulas and resistance formulas are same. Right? So CAB is 1 by summation of I is equal to 1 to n 1 by Ci, and whenever the capacitors are connected in series, the effective capacitance will be reduced and that resulting value will be less than the lowest value of the capacitors which are connected in series. You got the point? What about the voltage across each capacitor? What is the voltage across each capacitor? You know that Q is equal to CV. For series combination, charge is same. Therefore, voltage is inversely proportional to C. Therefore, V1 is equal to C2 by C1 plus C2 into V. V2 is equal to C1 by C1 plus C2 into V. It can be written as 1 by C1 by 1 by C1 plus 1 by C2 into V. It can be written as 1 by C2 by 1 by C1 plus 1 by C2 into V. Therefore, this is for two elements, but for n number of elements, this can be formula 1 by Ck by summation I is equal to 1 to n 1 by Ci into the total voltage. Next, parallel combination of capacitors. Simple, add them. The resulting capacitance will increase. The resulting capacitance value will increase. There was one question, it was asked in the gate based on this concept. Okay? Therefore, the resulting capacitance value is greater than the highest value of the capacitors which are connected in parallel. Star delta transformation. First I take delta to star. Same formulas as G Nana. Yesterday I explained. Please apply them. I don't want to explain anymore here. Delta to star to delta, same formulas. Conductance formulas are same as capacitor formulas. Coming to now inductor. Phi is equal to L into I, where L is nothing but n square mu A by L Nana. V of t is equal to L dA by dt. I of t is equal to I of t naught plus 1 by L integral t naught to t V of t dt. This is the power I of t into L di of t by dt. Energy, okay? The energy when you have initial current I of t naught, final current I of t, W of t naught initial energy 1 by 2, W of t naught plus 1 by 2 L into I of t whole square minus I of t naught whole square Nana. If I neglect this particular current, initial current, and neglect this initial energy, this is what the formula you will get. That is why we remember always half Li square, okay? Because we are neglecting W of t naught, we are neglecting I of t naught also, initial current also. Inductor is short circuit to DC. That is why inductor blocks high frequency signals, but it passes or allows low frequency signals. That is why we use the inductor in the filter circuits. Current through the inductor may not change instantaneously. That means, okay, and voltage across the inductor may change instantaneously. Current through the inductor may not change instantaneously. Voltage across the inductor may change instantaneously. Since current through the inductor may not change instantaneously, it means that discontinuous current through the inductor may not be acceptable. Continuous current may be acceptable. Discontinuous voltage may be acceptable. Like in the capacitor I explained, right? Okay. Series combination. Okay, ideal inductor does not dissipate energy, and practical inductor dissipates energy. The other 2 points also can be covered. Okay. Practical inductor means what, Nana? An inductor with a series resistor model. Okay, usually the resistance value is very, very smaller. Okay. Series combination of resistors, I told you that inductor formulas are same as resistor formulas. I don't want to elaborate anything here. Parallel combination of resistors, similarly. Okay, inductor formulas are same as what resistor formulas. Please go back to the previous session if you have any doubt in the formulas. Resistor formulas, inductor formulas are same. Okay. This is the current division method. Here flux division will take place. Phi k is equal to Lk by summation I is equal to 1 to n Li into phi in the series combination. Parallel combination, flux remains same but current divides. Series combination, okay, voltage divides means flux divides, current remains same. Okay, current remains same in the series combination but flux divides. Parallel combination, flux remains same but voltage divides. Therefore, LAB is equal to, okay, IK is equal to, current through kth inductor is nothing but 1 by Lk by summation I is equal to 1 to n 1 by Li into I is nothing but current flowing through the kth element. Delta to star, again I told you the resistor formulas and inductor formulas both are same. I don't want to spend time on this. Okay, you already had clear explanation in the previous session about the resistor formulas. The most important one for the transient analysis is initial conditions. The most important one is what? Initial conditions. Okay, so all of you pay your attention now. Very important discussion it is. Initial conditions in RLC element, when you see current through resistor and voltage across resistor may always change, okay, instantaneously. That is why they may change instantaneously means they are not same. That is why I am maintaining not equal to. VR of 0 plus is not same as VR of 0 minus. At t equal to 0, the disturbance is taking place. At t equal to 0 plus, immediately after the disturbance. At t equal to plus infinity, steady state after the disturbance. At t equal to 0 minus, immediately before the disturbance. At t equal to minus infinity, steady state before the disturbance. These are all pre-disturbance conditions. These are all post-disturbance conditions. At t equal to 0, the disturbance is taking place. You understand all of you? You understand all of you? At t equal to 0, the disturbance is taking place. Okay? These t equal to 0 plus conditions are called initial conditions. Initial conditions. Initial conditions, if you want to find, you must know t equal to 0 minus conditions in the inductor and capacitor, particularly current through the inductor, voltage across capacitor. Because current through inductor may not change instantaneously, voltage across capacitor may not change instantaneously. You got the point, all of you? Okay. Now, current through the inductor, current through resistor, voltage across resistor may change instantaneously. That is why 0 plus conditions are not same as 0 minus conditions in the case of resistor. But when it comes to the inductor, current through the inductor may not change instantaneously. Therefore, IL of 0 plus is equal to IL of 0 minus, provided the voltage across the inductor is finite. If the voltage across the inductor is finite, then current through the inductor may not change instantaneously. If suppose that voltage across the inductor is infinite, okay, infinite, nothing but what? No, ideal impulse. Infinite is nothing but what? Ideal impulse. Ideal impulse means what, Nana? Infinite magnitude in zero duration. It's nothing but ideal impulse. Suppose if I am here for a long time, that means I am in steady state. If somebody applies certain amount of force, finite force, okay, my body does not accept the sudden change in its displacement. Okay? Because it offers the inertia. You understand, all of you? Suppose the infinite amount of force is applied, it is predominate over what? The inertia offered by the body, then the body displacement may change suddenly also. When I apply sudden force, finite force, the body may not accept the sudden change in its displacement. When I apply infinite force, the body may also accept the sudden change in its displacement. Similarly, a body is nothing but what? A mechanical storage element. It stores the energy in the form of kinetic, right? But inductor stores the energy in the form of magnetic field. It is also having the inertia in the form of the current. When you apply the finite voltage, the current may not accept the sudden change. The current may not change suddenly. When you apply the infinite voltage, nothing but ideal impulse, suddenly ideal impulse, then the current through the inductor may change instantaneously. That is why, okay, IL of 0 plus is equal to IL of 0 minus when VL of 0 plus is finite. IL of 0 plus is not equal to IL of 0 minus when that VL of 0 plus is infinite, nothing but ideal impulse. VL of 0 plus is not at all equal to VL of 0 minus all the time. Clear? You understand, all of you? Is it clear, all of you? Okay. So I think I made it very clear, all of you. Is it okay? You got the points. Okay. Current and flux. Flux is directly proportional to current. So I can also apply the same formulas. Flux may not change instantaneously. Okay. Flux may not change instantaneously provided the voltage across the inductor is finite. Flux may change instantaneously if voltage across the inductor is infinite or ideal impulse. Clear? Coming to now capacitor. Voltage across the capacitor may not change instantaneously provided current through the capacitor is finite now. The same formula is applicable to what? The same statement is applicable to charge also. Charge deposited on the capacitor may not change instantaneously provided the current flowing through the capacitor is finite. If that current flowing through the capacitor is infinite, then the voltage across the capacitor may change instantaneously. That means the charge may change instantaneously. May change means not equal. Okay? If it is infinite, nothing but what? Ideal impulse. Ideal impulse. Is it clear, all of you? Is it clear, all of you? Okay? Well, but current through the capacitor may change instantaneously irrespective of the voltage across it. Current to the capacitor may change instantaneously. Got it, all of you? Okay? Now, most important assumption in the transient analysis is that until the disturbance takes place, the system was operating in steady state. That means what? Until the disturbance takes place. The disturbance is taking place at t equal to 0, Nana. Yes or no, all of you? So, until this disturbance takes place, okay, the system is operating in steady state. That means what? Minus infinity conditions and 0 minus conditions all are same. Okay? So, when somebody is asking you to find what is the 0 minus condition in the given circuit, you find minus infinity condition. Minus infinity condition is nothing but steady state. Under steady state condition, it is very easy to draw the circuit. Resistor remain resistor, inductor behaves short circuit, capacitor behaves open circuit. Under DC conditions I am talking about. Yes or no, all of you? You can solve the network easily by replacing the inductor by short circuit, by replacing capacitor by the open circuit. That's it, simple. Next, another important formula, when somebody is asking you what is the time rate of change of current flowing through the inductor at t equal to 0 plus, then VL of 0 plus by L can be applied. Similarly, what is the time rate of change of voltage across the capacitor at t equal to 0 plus? Please underline at t equal to 0 plus, then you can find by taking the ratio of IC of 0 plus to C. Okay, this is VL of 0 plus by L, this is IC of 0 plus by C. So now it's very clear how to construct the t equal to 0 plus equivalent, right? T equal to 0 plus equivalent circuit is to be constructed. How do you construct the t equal to 0 plus equivalent circuit, Nana? So why should I determine the t equal to 0 plus condition? Because I need the initial conditions all the time. Because the first most important question in the gate is that find t equal to 0 plus conditions. For that you have to construct t equal to 0 plus equivalent circuit. How do you construct? T equal to 0 plus circuit depends upon t equal to 0 minus conditions, Nana. What was the element at t equal to 0 minus resistor? At t equal to 0 plus also it becomes resistor. At t equal to 0 plus it is, okay? Please correct it. At t equal to 0 plus. It also becomes a resistor. Inductor, how it becomes? It depends upon what was the current flowing through the inductor at t equal to 0 minus. Sir, how do I find t equal to 0 minus current flowing through the inductor? I told you minus infinity conditions. Draw the equivalent circuit for minus infinity. Sir, how do I draw that minus infinity? Switching operation is not done. T equal to 0 minus means. Minus infinity means. Resistor remain resistor. Inductor short circuit. Capacitor open circuit. Find current through the inductor. Nothing but short circuit. That current is nothing but current flowing through the inductor at t equal to 0 minus. Based on that, the equivalent circuit at t equal to 0 plus can be constructed for the inductor. Got the point? Please watch my 5 videos. I spent enough time to make you understand in a very, very, very detailed manner. Don't miss those classes, I'm telling you. Okay? Well, you can also share those videos to your friends, community, okay? I'm sure that they will definitely enjoy the classes. I spent a lot of time because my specialization is, transient analysis. I'm expert in the transient analysis. I explain a lot of things in that particular transient analysis. Please go through all the videos. 5-6 videos are there. In my Telegram group, I will share once again. Okay, those videos. So, you found the current flowing through the inductor, let us say IL of 0 minus. Say in the first case of the inductor, it was found to be 0. There are some possibilities that the current flowing through the inductor was 0. If that is 0, at t equal to 0 plus, you replace it by open circuit. You replace it by open circuit. You understand all of you, Nana? Okay, you replace it by open circuit. Suppose if there was some current flowing, that is I0 at t equal to 0 minus, then you replace it by an equivalent current source with a parallel inductor model. This is an inductor, Nana. The parallel inductor model, this is what the inductor. Okay, current source must be there. Current is flowing. Some current was flowing at t equal to 0 minus. The same current should flow at t equal to 0 plus also. This current may not change instantaneously, with an assumption that voltage across the inductor is finite. Okay, this is what the equivalent circuit you are supposed to construct. Now, capacitor depends upon what was the voltage across the capacitor t equal to 0 minus. Okay, t equal to 0 minus means again minus infinity equivalent circuit, open circuit. Find the voltage across open circuit. That is nothing but voltage across the capacitor. If that is 0, then at t equal to 0 plus, it can be replaced by the short circuit. If that is not 0, some finite value V0, then it can be replaced by an equivalent voltage source V0 with a series capacitor model, that is short circuit. The series capacitor model, that is short circuit. Is it clear, all of you? Is it clear, all of you? Please respond quickly. Clear, all of you? Please respond quickly. Chandu, clear. Good. Any doubts, Chandu? If you have any doubts, please put in the comment box. Lakshmi and other people. Okay? Please respond. Very good. Good, good. Okay. Bindu Tarangini also clear, right? Very good, Nana. Any doubts, Nana, please do not hesitate. Put in the comment box or else share in the Telegram group channel, okay? Now, I would like to explain you simple two-step approach to determine the initial conditions, because in the gate, I think more than 60% of the questions have been asked so far on initial conditions only. Initial conditions are of two types, Nana. One is the normal initial condition, non-derivative terms like IR of 0 plus, VR of 0 plus, IL of 0 plus, VL of 0 plus, IC of 0 plus, VC of 0 plus. Okay? IR of 0 plus, VR of 0 plus, VL of 0 plus, IL of 0 plus, IC of 0 plus, VC of 0 plus. Do you understand, all of you? Okay. These are all non-derivative. Derivative terms are nothing but di of 0 plus by dt, dv of 0 plus by dt. You understand, all of you? These are the derivative terms. Okay. Well, now the two-step approach is very simple to apply. Usually he will ask you the questions either the non-derivative terms or first derivative terms. Second derivatives are also there. D square I of 0 plus by dt square, d square v of 0 plus by dt square. Like that also you have. Second order, higher order derivative terms are also there. But usually 99% the questions will be asked on the first derivative terms. That too, d I of 0 plus by dt, where I is current flowing through the inductor, dv of 0 plus by dt, where v is the voltage across the capacitor. Usually the questions will be asked on all these. I mean these only. Okay. And you will also be asked the questions on VL of 0 plus, IC of 0 plus, IR of 0 plus, VR of 0 plus, most probably. You know, very simple questions in the 1 mark will be asked on IL of 0 plus and VC of 0 plus. Because straightforward, IL of 0 plus, VC of 0 plus is very easy to find. So all these things, how we find, let us understand. These two steps are enough to understand how to find those quantities. The first step is, first you construct t equal to 0 minus equivalent. Because if you want t equal to 0 plus conditions, you must know what was the current flowing through the inductor t equal to 0 minus, and also what was the voltage across the capacitor t equal to 0 minus. These two are very, very important quantities, okay, in step 1. You understand, all of you? In step 1, these two are very, very important quantities. Now, when you find IL of 0 minus and VC of 0 minus, you can immediately conclude that, IL of 0 plus is equal to IL of 0 minus. VC of 0 plus is equal to VC of 0 minus. Suppose in the exam, he is asking what is the voltage across the capacitor in the following circuit means. In the first step itself you are getting, because 0 plus conditions are same as 0 minus conditions, Nana. Current through the inductor is asking IL of 0 plus is equal to IL of 0 minus. In the first step itself you are getting. But other than these two quantities, what are those two quantities? Tell me. Current through inductor, voltage across capacitor. Current through inductor, voltage across capacitor. Other than these two quantities, if suppose any question is coming, you have to go for step 2. For that step 2 is nothing but constructing T equal to 0 plus equivalent. How do you construct T equal to 0 plus equivalent, Nana? How does it look like? Tell me. T equal to 0 plus means switching operation happened. I start from the switching operation. Switching operation happened. Yes or no? Resistor remain resistor. Inductor, take a break. It depends upon what was the current flowing through the inductor at T equal to 0 minus. If that current was found to be 0, then at T equal to 0 plus it becomes open circuit. If that current was found to be non-zero, some 10 amperes, 3 amperes, 5 amperes, it will become what at T equal to 0 plus? An equivalent current source with a parallel inductor model. Clear? Just now we have seen the table. From the table it is very clear. Sir, capacitor, it depends upon what was the voltage across the capacitor T equal to 0 minus. Sir, where was that value? In first step only you determined, right? Don't worry, you already got that value with you. You already got that value with you, right? So based on that, you are going to construct T equal to 0 plus equivalent. If that voltage across the capacitor was found to be 0, then at T equal to 0 plus, the capacitor will be replaced by a short circuit, right? If that voltage was found to be some non-zero value, 10 volts, 5 volts, minus 20 volts, replaced by an equivalent voltage source with a series capacitor model. In table, I made it very, very clear. The table was very clear. The table was very clear. 2 cases in the inductor, 2 cases in the capacitor. That's it. Clear? Clear all of you? Okay, well, now, this is how to find the initial conditions I explained. Now, how do you find the time response of RLC circuits? Time response is nothing but what, Nana? As a function of time. That's it. Either it is voltage or current, anything it might be. Once you know current and voltage, you can find the power. Yes. Sudhir Gupta, you are saying 0, Nana. Yes. What is that 0? I think you are talking about the voltage across the capacitor and current through the inductor, right? Okay. Well, now, tell me here, how do you find the time response? Maybe for first order circuits or second order circuits. Okay. For first order circuit or second order circuits. There are 2 types of circuits you come across in general. Okay. There are 2 types of responses also you will come across in general. 2 types of circuits, 2 types of responses. You're following? Okay. What are those 2 types of circuits, Nana? First order circuits and second order circuits. What type of 2 responses you have, Nana? When you give step input, that response, the resulting response is step response. Okay, when you give other than step response, it is a non-step response. Maybe sinusoidal, exponential, shifting functions, impulse input you are giving to the circuit. Then the resulting response is not step response, right? It is a non-step response. So 2 types of circuits you have, you can classify easily now. First order circuit and second order circuit. 2 types of responses you have, step response, non-step response. So first order circuits with step response means step input excitation. First order circuits with non-step input. Second order circuits with step input. Second order circuits with non-step input. These are all different varieties of circuits you will come across in the transient analysis. In the exam point of view, I'm teaching you now here that these are the 4 different cases you will get. First one is what? First order circuit with step input. Second one is what? First order circuit with non-step input. Non-step means what? Maybe ramp, parabolic or impulse, shifting functions, exponential, sinusoidal, anything it might be. Now, third one is what? Second order circuits with step input. Fourth one is what? Second order circuit with non-step input. Second order means L and C. First order means only either L or C along with the resistor. Clear all of you? Is it clear all of you? Okay. Now, the first type of circuits we can solve, that is first order circuits when they are excited with the step input, the two important formulas can be applied. The first formula is valid when the switching operation is taking place at t equal to 0. The second formula is valid when the switching operation is taking place at t equal to t naught. T naught is some delayed time. The time delay is taking place. Instead of t equal to 0, you are applying the switching operation at t equal to t naught. At t equal to 0, when you apply the disturbance, the response after the disturbance taking place in the system, the response is I of t is equal to I of infinity minus the whole bracket, I of infinity minus I of 0 plus into e power minus t by tau, where tau is nothing but the time constant for the first order circuit is L equivalent by RTH, or if it is a RL circuit, if it is an RC circuit, C equivalent into RTH. You understand all of you? Okay? C equivalent into RTH. This is how you determine. But whenever you determine this tau value, okay, remember you must find the tau for t greater than 0. That means RTH and L equivalent, C equivalent, RTH must be calculated after the switching operation, not before the switching operation. Second formula. When the switching operation is taking place at t equal to t naught, then I of t is equal to I of infinity minus I of t naught plus, because switching operation is taking place at t naught na, then immediately after the disturbance takes place or immediately after the switching operation takes place, nothing but t naught plus into e power, this is e power nana, okay, there is a mistake done, okay, e power minus t naught by tau, again tau is nothing but what nana, L equivalent by RTH and C equivalent to RTH, those values must be calculated after t naught, after switching operation. Okay, this is what the formulas, simple formulas that can be applied for first order circuits when excited by the, step input. Now, other than this particular case, any case that you come across, first order circuits excited with the non-step input, second order circuits excited with the step input or non-step input, okay, 3 different cases, right? Total 4, out of which first we have seen, all other 3 will be coming under the second category of the problems. Those problems can be solved by S-domain equivalent circuit. That means using Laplace transformation. Is very clear. Using Laplace transformation. Got it all of you? Okay. Well, when you are using Laplace transformation, better you construct S-domain equivalent circuit. That means a time domain circuit is given to you. You are converting that into S-domain for your convenience. Okay. Then you are finding the response in S-domain, means I of S, V of S, something like that. Then you are applying inverse Laplace transformation to that. Apply the partial fractions, which is of course a little challenging task, but there is no other option for you. Okay. There is no formula directly available. You have to apply the S-domain equivalent only, Laplace transforms only. Then apply the inverse Laplace transformation, then get the response in the time domain. Got it? A time domain circuit is given to you. Temporarily you are converting into S-domain by applying Laplace transformation. How to construct that S-domain equivalent circuit I will tell you now. Don't worry. Then find the response in S-domain. Then apply the inverse Laplace transformation with the help of partial fractions. Then find the response in time domain. That is your final response. So what kind of circuits you are going to handle here? Tell me using the Laplace transformation. Tell me all of you. What type of circuits you are handling? The first order circuits with non-step excitation. Second order circuits with any excitation. Whether step or non-step doesn't matter. All those will come under another category, second category of the problems. Those second category of the problems will be handled by the S-domain equivalent circuit. First category of the problems are nothing but what first order circuits excited by the step input. Those problems can be solved by simple formula. Just now I explained there are two formulas based on the switching operation, t equal to 0 or t equal to t naught. You can apply the formulas. The formulas are applicable only for the first order excited by the step input. That's it. Other than that, S-domain equivalent is important. Okay? Yes, second order circuits, Nana. Gupta. Sudhir Gupta. Exactly. Second order circuits. Okay. So now, what are the S-domain equivalent? This is a time domain. This is a S-domain. R remains R. R remains R. This S-domain must be constructed for t greater than 0 because your interest is to find after switching operation, right? Therefore, yeah, first order non-step inputs, second order circuits can be solved by S-domain equivalent. Very good. That is true. But first order with step input can be solved by method 1, that is formula. Method 2 is what? S-domain equivalent circuit. Okay. So inductor, the equivalent circuit in S-domain is Ls in series with the voltage source. Clearly look at this. If current is in this direction, the voltage polarities are in this with these polarities, then the polarities of this voltage source which is in series with this Ls must be, it is minus and plus. It must be very clear. And its value is L into IL of 0 minus. What is IL of 0 minus, sir? You have to construct t equal to 0 minus equivalent, then find that IL of 0 minus. Without that, you cannot construct. Most of the times, you know, L means, most of the people remember that it is Ls only. That means they are neglecting IL of 0 minus. They are neglecting IL of 0 minus. You can't neglect in this particular case. Got it? Sometimes it might be 0. If you get in 0 by finding the value, there is no problem. But you can't take it 0 by default. You have to find that value. So L into IL of 0 minus. Clear? Well. Now a voltage source with a series impedance, because this Ls is nothing but what? Reactance, right? Reactance or impedance, whatever you can call it. A voltage source with a series impedance can be converted or can be transformed into current source with a parallel impedance. Therefore, look at this based on the polarities, I am taking the direction of the current like this. And L into IL of 0 minus by Ls will give you IL of 0 minus by S, and Ls remain Ls. Source transformation I am applying here. One mark questions may be asked on these equivalent circuits also. You must be very careful. Equivalent circuits, S-domain equivalent circuits of RLC elements must be on your fingertips. You can't again search in the exam. You can't do research in the exam. It's very clear. Ls with voltage source minus plus polarities with the current direction, based on the current direction. C, capacitor, only 3 elements, RLC, right? C, 1 by Cs with the polarities are plus minus. I maintain the plus minus polarity same, but this value is Vc of 0 minus by S. So what is Vc of 0 minus, sir? I have to find it at t equal to 0 minus equivalent circuit. T equal to 0 minus equivalent circuit is very, very important. You understand? Both in case of t equal to 0 plus equivalent circuit construction and also in S-domain equivalent circuit construction. Got it? Okay, well. So now, using source transformation again, Vc of 0 minus by S divided by 1 by Cs, Ss will get cancelled. C into Vc of 0 minus, that is what you got here. Based on the polarities you got, these polarities are exactly reverse to the polarities of the voltage that appears in the inductor case. Inductor case minus plus, capacitor case plus minus, and the current source is now based on the direction of the polarity, based on the polarities of the voltage source, the direction of the current can be indicated when you are going for the source transformation, right? So this is what I am doing. This is 1 by Cs remain 1 by Cs. Okay. So this is all about now first order, second order circuits to solve. Okay. The simple techniques, simple formulas I have explained. Okay. For RLC circuits, initial conditions, time response. These are the two cases you come across in the exam. Got it? The videos I will share you, and if you have any problem, in receiving, please join my Telegram group, Professor Muninder Gate. I will share these videos. And yesterday's PPT and this PPT, I will share you today. Don't worry about that, okay? Because I need to just convert that into PDF, and the size of the PPT is very larger. I need to convert and reduce the size, and then I will send you in the Telegram group only. Understand, all of you? In the Telegram group, I will send you definitely. Don't worry about that. Okay? Well, are you following, all of you? Shall we move on to two-port networks now? Very simple two-port networks formulas. I think I don't have anything to explain, but quickly I will go through it, some important cases. Okay? Please respond quickly. All of you following or not? Tell me first. I should understand whether you're following or not. Chandu, okay. Bindu Tarangini, okay. Bhaskar Lakshmi, okay. Very good. What about the remaining guys? Are you okay with that? Well, let's move on now. Two-port networks, okay? Z parameters, equations, I think these relations must be printed in your mind, I'm telling you. You can't take any chance, okay? Yes, the relations must be very clear. Voltage is expressed in terms of currents, Z parameters. Currents are expressed in terms of voltages. You will get Y parameters. Clear? So Y is always what? Inverse of Z matrix. Suppose if Z11 is equal to 10 ohm, what is Y11, Nana? Can you please tell me? All of you please respond quickly. If Z11 is equal to 10 ohm, then what is Y11, Nana? Can you please quickly respond? Can you please quickly respond? Can you please quickly respond? Bhaskar Lakshmi is saying 1 by 10. Anybody quickly? I want a quick answer from you. I want a quick answer from you. If Z11 is equal to 10, what is Y11? Quickly, all of you please respond quickly. Bhaskar Lakshmi, you answer my question. Suppose Z matrix is 10, 5, 5, 10. Okay. What is Y, Nana? Z inverse, right? Okay. Z inverse, right? Bindu Tarangini is saying minus 10. Let me check. Look at this. 1 by Z inverse means matrix inverse you are supposed to find. You can't really take a, okay, inverse for this particular parameter alone. This is simply a parameter, that's it. Parameter to parameter, you are not supposed to take the inverse, Nana. Matrix inverse you are supposed to take. So 10 square minus, okay, 10 into 10 minus, okay, 5 into 5. This is minus 10. Okay, sorry, this is 10 again, and minus 5, and again 10. Is it clear? Now, tell me, 100 minus 25. 100 minus 25 means 75. So 10 by 75 minus 5 by 75 minus 5 by 75, 10 by 75. So what is Y11? 10 by 75, not 1 by 10, Nana. I hope you understand the point. Clear? Okay. Sometimes we do mistakes, okay, in the exam in a hurry manner. We may not even think of, because impedance means reciprocal of admittance, admittance means reciprocal of impedance. Don't get confused, okay? Always apply inverse to the matrix, not to the individual parameter. Transmission parameters, V1, I1 in terms of V2 minus I2, ABCD parameters are transmission parameters, okay? ABCD parameters and transmission parameters both are same. Inverse transmission parameters, not. Now V2 minus I2, I'm taking V2 I2 here, but V1 I1, V1 minus I1 I'm taking here, that's it. So inverse transmission parameters are always inverse of ABCD parameters. Simple. Hybrid parameters, V1 I2 in terms of I1 V2, you will be getting H11, H12, H21, H22. Inverse hybrid parameters, I1 V2 in terms of V1 I2, G11, G12, G21, G22. G parameters are always inverse of H parameters. Basically, there are only three types of parameters. One is Z parameters, the other is transmission parameters, the other is H parameters. When you apply inverse to this, you will get Y parameters. When you apply inverse to this, you will get inverse transmission parameters. When you apply inverse to this H parameters, you will get inverse hybrid parameters or G parameters. That's it. There are only 3 types of parameters. When you apply inverse to each, then you will get other 3 parameters. You understand, all of you? Other 3 types of parameters you will be getting. Okay, condition for symmetry in terms of Z parameters is Z11 is equal to Z22, Y11 is equal to Y22, A is equal to D, DH is equal to, delta H is equal to 1. Delta H is nothing but what, Nana? Determinant of H matrix, nothing but H11, H22 minus H12, H21 should be 1. This is nothing but what? Delta H is equal to 1. Hope you understand this. This is actually called condition for symmetry. Okay, delta G is equal to 1 is also condition for symmetry. A dash is equal to D dash is also condition for symmetry. I am not writing, but there is also implied. Condition for reciprocity is nothing but Z12 is equal to Z21, Y12 is equal to Y21, AD minus BC is equal to 1, A dash D dash minus B dash C dash is equal to 1, H12 is equal to minus H21, G12 is equal to minus G21. Yes, condition for reciprocity. There are totally 6 types of parameters we have. Okay, we can find condition for symmetry and condition for reciprocity using these relations. These are all conditions. Now, another most important thing in the two-port networks is that interconnection of two-port networks. You can connect the two-port networks in series. Okay, series combination means there are two-port networks are connected in series, something like this. This is what the series combination. Okay, there is a parallel combination. How do you find the parallel combination? Something like this. Okay, join these two, one port, join these two, another port. Similarly here also, join these two, you will get one port, join these two, you will get another port. These two are said to be in parallel combination. Cascade combination. What do you mean by cascade combination? This is the cascade combination. This is a cascade combination. Output of the first network is given as an input to the second network. These two are the ultimate 2 ports. So this is what the resulting 2-port network, this is what the resulting 2-port network, this is what the resulting 2-port network. When 2 elements are connected in series, it can be replaced by a single equivalent element. When 2 2-port networks are connected in series, it can be replaced by a single equivalent 2-port network. When 2 2-port networks are connected in parallel, you can replace by a single equivalent 2-port network. When 2-port networks are connected in cascade, okay, they can be replaced by a single equivalent 2-port network. So that is nothing but interconnection of 2-port networks. So the first connection is what? Series combination of 2-port networks. When 2-port networks are connected in series, usually the Z parameters are more comfortable or convenient to express. The relation is readily available. The resulting 2-port network Z parameters will be equal to summation of Z parameters of individual 2-port networks. Okay, next. Parallel connection of 2-port networks. The Y parameters of the resulting 2-port network when n number of 2-port networks are connected in parallel. First one is what? When n number of 2-port networks are connected in series. The second one is what? When n number of 2-port networks are connected in parallel, then the resulting Y matrix will be sum of the individual Y matrices of the individual 2-port networks which are connected in parallel. Got it? Cascade connection. Instead of summation, in the cascade connection, you must multiply the transmission matrices of the individual matrices. There are n number of 2-port networks connected in cascade, then the resulting 2-port network, when you replace all this combination by single 2-port network, the resulting 2-port network transmission parameters will be equal to the product of individual transmission matrices. That's it. You understand, all of you? Similarly, hybrid connection of the 2-port networks. Hybrid combination means Input side series, output side parallel combination can be possible. Input side parallel, output side series combination is also possible. So input series, output parallel, the first combination can be taken as hybrid parameters, H parameters we will generally take. That is nothing but hybrid parameters. H matrix is nothing but resulting H matrix is sum of H matrices of the individual two-port networks when n number of two-port networks are connected in hybrid combination, input side series, output side parallel. Got it? Similarly, the second type is input side parallel, output side series. Then the resulting G matrix is summation of all G matrices when n number of two-port networks are connected in hybrid combination with input side parallel, output side series. You know series and parallel just now I have explained, right? Okay, input side series, this is input side series, output side series, therefore it is called series combination. Input side parallel, output side parallel, therefore it is called parallel combination. But input side series, output side parallel, it is called hybrid. Input side parallel, output side series, then it is called hybrid. Then the two-port networks can be replaced by a single equivalent two-port network. Those two-port network parameters will become now, in the first case H matrix, in the second case what? G matrix. Series combination, G parameters, Z parameters, parallel combination, Y parameters, cascade combination, transmission parameters, hybrid combination, H parameters and G parameters based on series parallel or parallel series. This is what end of the two-port networks. I hope you enjoyed the session, all of you. Okay, I'm going to wind up today the session. I discussed DC circuits, AC circuits, transient analysis, two-port networks. Some topics are left over, like, the magnetic coupled circuits, Nana. Okay, it's a very simple topic. Okay, I don't have to discuss those things at all. I think you can manage on your own. So I discussed the major important topics in the exam point of view, which will really going to help you a lot. Okay, so please quickly respond in your comment box whether you enjoyed the session or not. Okay, it will be definitely going to be a great motivation for all the faculty, especially for me. Okay, I'll be definitely doing some more important videos in the near future, more and more videos in the near future, which will definitely help you a lot. Understand, all of you? I told you already my Telegram group, Professor Muninder Gate. You join this, I'm sure I will help you out if you have any doubts. Network theory, controls and power systems, any subject. Okay, if you have any doubts, I can definitely clarify. Understand, all of you? I'll share you all the videos. I will share you all the videos, again, whatever I've done in the transient analysis in the Telegram group. Okay, you please watch them. I'm sure that you will definitely enjoy, because each and every point I've explained in that particular session. Okay, thank you so much. I think I see Bhaskar Lakshmi, you're waiting for another important session. Okay, I will definitely do, Nana. Okay, keep doing well. Always, spend a lot of time on your study hours. Get up in the morning, okay? Spend some time, prepare well. You definitely get very good score in the GATE examination. Once you get a GATE, once you get an admission in IIT, I'm sure that you're going to get wonderful jobs with higher packages. Don't compromise. Put your effort. It's a one-time effort in your lifetime, I'm telling you, okay? Bhaskar Lakshmi, Bindu Tarangini, yeah, you can expect very soon a numerical session. I will try, because I need to check with my team. Okay, yeah, I will. I can't find in Telegram group. Okay, you can connect with me. Connect to me in the mobile number 9866 546088. Please text me if you face any problem. Okay, yeah. Yes, sir. Hey, Nasuma, I'm unable to read some names. Okay, don't mind. Sudhir Gupta. Okay, thank you so much, all of you, for your nice comments. Okay, and we will meet very soon. Thank you and all the best, all of you. Bye-bye. Take care, all of you.